Thank you very much. Thanks a lot, Sebastian. Great name for the introduction. Let's have a look at some of these announcements that you just mentioned. So every week almost there's something new in the press. Microsoft, we just discussed, is back in topological qubits doing Majoranas, or at least looking at that. Then recently just this announcement from PsiQuantum regarding the Series E raise of 1.5 Australian dollars. So really impressive numbers apparently. There's a lot of things ongoing in quantum, and every few weeks there's a new announcement and the quantum era has finally begun. It's really fun looking at the press here, there, and that's why we're here, right? In order to see or to analyze how is there a gap between the announcements or the performance of quantum computers and the need of the users of the application. And as just also discussed, we are not doing this alone. So I'm from Infineon. We are not looking at this on our own, but we're joining forces in a consortium called QUTAC, so Quantum Technology Application Consortium, where together with large German corporates, we join forces here, the expert knowledge of the various groups to create a critical mass and really look into the various applications which are relevant for the German industry. Because that's exactly where the German industry is very strong at, right? We have all the big corporates which have all the use cases which should benefit in the end from quantum computing. So these are the right people to talk to really get a pulse on where are we with respect to quantum computing. And one of the early things, of course, which you realize when you're going into this topic, you read a lot about number of qubits, but number of qubits is not the only thing which is relevant in order to assess even the physical parameters of such a system is much more, right? So it's, of course, number of qubits is very important. It determines the problem size which you can address. But also the qubit quality is very, very important in order to address the problem complexity. And not to forget the solution time, because in the end, it's not about theoretical speed up, exponential speed up in quantum. It's about speed up in real use cases. And for that, I don't care about 10,000 times faster solution if it still takes 3 years to solve it instead of 30,000 years. I really need the solution in a short amount of time to apply this within the company. And very much looking forward also to one of the panelists. But just to give an example here from Boehringer, what really matters is the physical or the clock runtime for the solution which you want to address. They did a couple of years ago an assessment, and I just want to point to this value here. So it took for this solution, the estimate 3 days in order to come up with a solution for a single data point on this protein with quite some huge numbers of logical qubits and number of gates. Of course, now there are much more recent analyses and works further improving that, but it just shows, hey, that's a requirement, that's a target which we have to aim for regarding number of qubits and number of gates, and this has to happen at a reasonable runtime, and days, weeks, or months is not reasonable. I need this much faster. So therefore, what we have to work on is coming closer, bridging the gap from 2 directions. So of course, one is, now here again, the parameter is the number of physical qubits, is improving or increasing the number of physical qubits in order to increase the problem size which I can address, but at the same time also work on the algorithms, on the approaches, also on the implementation in order to reduce the requirements on the hardware to really bridge here the gap between the applications, the requirements from application point of view for economically relevant applications, and the performance of quantum computers. And that shall be exactly the topic of today's panel, and therefore I'm very much looking forward to the discussion, and let me welcome on stage Dr. Nikolaj Moll, he's a quantum computing scientist at Boehringer Ingelheim, responsible for algorithms for pharmaceutical research and development, and had been before at IBM Research. Please, warm welcome to him. As another representative for the user community, I welcome Dr. Marvin Erdmannm from BMW. He is quantum solution engineer and responsible for the open source benchmarking framework Quark. I love this name. Thanks. Now, for the your supplier side, let me welcome Dr. Ulrich Meier from IQM. He's business development manager. Welcome on stage, Ulrich. Thank you. And last but not least, Dr. Stephen DiAdamo, co-founder and CTO of Qoro Quantum, which are looking into the software stack for distributed and hybrid quantum computer. And before he had been at Cisco Research. Welcome. Thank you very much. Yeah, so let's start perhaps with the current state of the art, and let me address the first question to you. Ulrich, how would you honestly describe the current state of quantum computing in terms of readiness for real-world applications?
Yeah, good afternoon, and I stick to the motto, no bullshit today. So the truth is that we are still in the NISQ area, so we are still in the noisy intermediate scaling area, and to my best knowledge, that's also true for our competition. So nobody has real functional logical qubits that could interact yet. And to my knowledge, we are on a good track, but we are about 5 years away from that. So, but it's a bit different than it used to be before, and it's not like nuclear fusion where it's always 50 years ahead. If you look at the roadmaps from various companies, they all kind of converge that the logical qubit set will be there by the turn to the next decade.
Very good, very good. I love that approach. So for fusion, it's 10 to 15 years, and for quantum, it's always 5 years. Excellent. Thank you very much. Yeah, now, looking at BMW, for example, so what are your expectations in terms of performance, scalability, and ease of use towards quantum computers?
I mean, as I just said, we are in an era where we are really looking on what are the actual problems that we need that we need quantum computers for, right? That's the first problem that we really need to understand. And as soon as we find these use cases, we then obviously expect some sort of improvement in the quality of the solution, the runtime, but also costs at some point, right? Like eventually, quantum computers will hopefully not only be faster and solve larger problems, but also hopefully more cost-effective. Right, and I think this is, as you said, probably a couple of years away, but a couple of years is really not that much if you think about it, and we really need to work on understanding the technology right now and understanding, as I said, the use cases for it, so that we are ready when the Q day comes in a couple of years.
Excellent. Q day is coming. To get perhaps the perspective from a pharmaceutical company here as well. So, Nikolaj, do you think the promises made by quantum providers, everybody on stage excluded, align with what your company actually needs to solve your most challenging problems?
Yeah, so I think there are certain providers who look at the full stack. So, I mean, one of the providers you mentioned, like PsiQuantum, and also Google, I think with them it's very good to work with because they look at the full problem. I mean, from hardware, error correction, and then algorithms. And so we believe we really have to go to the fault-tolerant regime to get any industrial advantage, because we need exact numbers and we cannot do it in NISQ. So we're looking at fault-tolerant algorithms, and so we need also partners which look at how to implement fault-tolerant algorithms on their hardware. And I think that's missing a little bit right now in the situation. So you have a lot of hardware providers who look mostly just in NISC, but it would be in Europe better to have more hardware providers which would look also at fault-tolerant quantum algorithms. One of the providers is Quantum Motion, which we are working in the UK with them, and they also look at fault-tolerant algorithms. And I think this has to happen more, because if we would have today a fault-tolerant quantum computer, we wouldn't have anything to run on it. So in line with the hardware development, we have to also develop the algorithms. And as soon as we have small machines, I think this will go faster, because then we can do real development of our algorithms on these machines.
I see. Okay, so it's fault tolerant then. Yeah, so talking about exactly the full stack. Question to you from Qoro, Stephen. So how do you ensure that the entire stack is really optimized for real use cases, so really matching what the users need?
Yeah, so our perspective is we don't think quantum computers will work alone. I think no one is saying this anymore. And we also don't think there'll be single quantum computers working monolithically. So our perspective is to try to optimize in a horizontal way, or try to scale horizontally for now, because other people are looking at the vertical scale. So making bigger quantum computers, but also making copies of those quantum computers, putting them side by side with classical computing infrastructure. And now the perspective is, how do we get users to use that type of infrastructure and make it easy for them to use that infrastructure? And that requires software, and nice clean software, not, all the way at the application layer, all the way at the hardware layer. There needs to be something in between, the middleware, of course. And this is what we tried to solve at Qoro, is make this as easy as possible. Take away the hardware knowledge, take away all of the necessary knowledge about the infrastructure away from the user, so that they can think about the problem and not how to scale it to 10 devices, and use GPUs as well, and use CPUs as well, and scheduling and making sure everything is working nicely. Orchestration has to be abstracted away.
Okay, so it's independent from the hardware layer below?
So it's exactly, it sits right in the middle, hardware, software, middle.
Okay, I see. Yeah, thanks a lot. Perhaps going back to you, Nikolaj, so do you feel that the quantum providers are really addressing your needs as end user, especially across the whole stack, or is there somewhere a gap? I mean, in software, in ease of use, is there something which you're still missing, despite the fault-tolerant quantum computer, of course?
Yes, I think there also in the software, there's still a way to go. I mean, there are these experimental tools like Qualtron from Google, where you can estimate run times and number of gates, but it's all very hard to use because it's very, very research driven still, all these tools. And I think the ease to use should be improved in these tools, that more people can use these tools and then estimate how fast certain algorithms will run if we have the quantum computers at a certain point.
I see. So do you still have to be a quantum physicist in order to use these kind of tools? Or
I think yes, in principle, or quantum physicist, theoretical physicist, or mathematician or so.
I see. So lucky the company who has these. Actually, we have some of them, they're sometimes called quantum sleepers in the company, so they're doing something else and we try to pick them. Perhaps exactly going back to this topic, no bullshit. So going back to a provider, IQM superconducting quantum computers, impressive performance. So while quite some, or a few quantum algorithms have promised the exponential speed up, of course, when you want to implement them for real use cases, many challenges arise. So how do you address these challenges?
Yeah, first let me maybe answer to Nikolaj's question. I mean, we're also working on an interface that's more abstract. So we're trying to lift the abstraction level by implementing CRISP as an interface which not operates on gates or qubit, but operates on quantum variables. So that's kind of, that's one aspect that we're working on. And the other aspect on scalability is, of course, that for some algorithms, the scalability just kicks in when the quantum computer is sufficiently large. So that's, for example, for factorization Shor's algorithm. That's the case, you need a number of logical qubits. So in the meantime, we have to focus on NISC algorithms which allow some kind of faulty results, and that could also be quantum chemistry, yeah, where you do something like complete SCF in quantum, which really is not that susceptible to numerical errors. Yeah, that would be something in the meantime.
Okay, as a stepping stone to the
as a stepping stone to fault tolerance. Of course, the holy grail is the fault tolerance, and we're working towards that. But then there also is an aspect of politics. I mean, you cannot just, let the market regulate that over more than a decade or even 5 years. There has to be some, public interest if you want a European quantum computer solution. The Europeans have to basically at least partially fund that and not just say, oh, here's the greenhouse, it'll grow. No, that's unfortunately not the case. The other competitive regions will put in a lot of efforts and a lot of money. So Europe and the European economy has to act here.
I see, yeah. Yeah, I heard of that other regions are active there as well. Yeah, Marvin, so yeah, I assume that you're very often approached by quantum computing companies to talk about use cases. So have you ever experienced a disconnect between the marketing statements and the real performance there?
I mean, we already heard a couple of words about how we actually evaluate the performance of quantum computers, right? And I think this is really where where one super important aspect comes into play, which is benchmarking, right? And open source benchmarking. We at the BMW Group had a couple of years the idea that there should be a tool for that, which is Quark. And this is a tool that tries to avoid what Nikolaj just said, that you need to be a quantum physicist in order to actually run benchmarks, because we are looking at the application-oriented benchmarks, right? So we are really looking to provide a tool that allows you to just add your own individual pipelines and use whatever algorithms and hardwares you like to use, but compare the performances in terms of the actual use case that you are running. And I think this is one way to avoid this disconnect between what is promised and what you really can achieve. If everything is transparent, if everyone can reproduce the results using the same parameters, using the same data sets, I think this goes a long way that everyone actually trusts the promises that providers make, and also the technological roadmaps, right? Because this is, I think, the second thing I want to mention here is that we really need reliable technology roadmaps by the provider, so we can more or less for sure tell what comes in 2 years and 3 years, and eventually at the end of the decade, hopefully the first fault-tolerant quantum computers as well. This is, I think, the core to it.
I see. And Nikolaj, how do we do it in Boehringer? I mean, do you also use kind of a benchmarking, or do you rely on the information from providers, or how do you assess in order to
so one of the slides you shown, so this was work with Google together, yes. And they benchmark it for us in principle. They counted the gates. I mean, now they have their software also to do this, and they get the same numbers. And mostly we do it with partners and look at different types of scaling. Sometimes it's big O scaling, so it's just, if you would have a really big system, would it be faster, or how does it scale exponentially or not exponentially? And sometimes we also count the gates, but I mean, we cannot run it, so it's mostly just counting the T gates at the end, how many there are, and they're normally around 10 to the 9 always. That's the number of what starts for small quantum machines. Okay. So it will always be like an hour or two to run the first algorithms on small machines, where you would have like 1,000 logical qubits. And this is mostly how we do it now, but it's very research-driven still, and it would be nice also to get this with new tools than to be more automatic for systems.
I see. So these are the numbers, 10 to the 9 and roughly 1,000 logical qubits. That's what you need in order to be successful. I see. Okay. Well, still a way to go, I think. Yeah, but this is now the view from the users, from the people really applying this. And so, coming back to you from Qoro, so what kind of feedback do you seek from the customers in order to build systems which are useful for them? I mean, it's a fascinating technology, right? But in the end, they have to pay for it. Otherwise, we are all in trouble.
Yeah, the main issue we see now is being able to at least prototype problems to a size bigger than a little toy problem. So generally they can simulate 25 qubits, but when you go on a problem that's represented in 25 qubits, it's very small, it's hard to make any predictions based on that problem. And so what we need to see is like, how can we do more with what we have? You know, how can we extend this to 100 qubits, but thinking in a different way? And our approach is to take it a partitioning of the problem. You lose the full scope of the problem because you break it into pieces, but at least you can go beyond what's possible with 25 qubits. So for example, we can take these optimization problems, break them into pieces. And this allows our customers to go a little bit further than what they can do now. It's still not a full quantum solution, but at least it pushes to a level where now it's not just 25 qubits, that's maybe such a small problem, there's no information there. If you go to 1,000 qubits, partitioning the problem up, okay, it's a bad solution, but now you can start doing something again. So it's at this point now, I think with most customers where they're satisfied with a 25 qubit solution, they can maybe do a little bit of noisy hardware simulation, but still you want these 1,000 qubit solutions and you can't get that without breaking things down today at least, before we have those 1,000 qubit devices. So our customers are really stuck at how do we get further than this? We're in this valley of emptiness where there's nothing to do until the quantum computers come, but there actually is, if we think about it in a distributed way.
I see. Okay, yeah, coming back to one of the perhaps controversies, quantum supremacy had been a term which generated excitement but also skepticism. So you're asking again, you Ulrich from IQM, so how do you ensure a realistic communication? I mean, that's a challenge, right? Of course you have to promote the capabilities which your system already have. On the other hand, you have to be cautious not to overhype progress. So what's your approach there?
I think it's a fine line between promoting and hyping the system. Of course, the supremacy or we will have quantum advantage here and then. I think that's a hype for sure. I mean, we won't wake up one morning and poof, there's quantum advantage. I don't think there's a Q day. I mean, there will be a few years where it will be an awakening or a sunrise for quantum, which will take a couple of years for sure. I mean, it's not something that comes, overnight or not even, within half a year. It will be a process for sure. However, I think we're closer to that than in your initial slide, you showed the chemistry example where there were, if I remember correctly, 1,400 logical qubits, but 4 million physical qubits, and that's an overhead factor of more than 2,000. We have a quantum error correction code that bring down that overhead more than 1 order of magnitude. And that 1 order of magnitude, like factor of 10, that's 2 generations, so it might come like 5 years earlier than anticipated on your slide. So we're on the track, but it won't come overnight. It will come for various applications first, and then for some examples, and then there will be, of course, a threshold on the size that the early fault-tolerant quantum computers can digest.
I see. Okay. So it's not a single Q day?
No, unfortunately not.
Yeah. Some years.
Bad for my stock options, but
No, then there's a continuous rise. It's also nice to look at, right, every day.
Exactly.
Can I also comment on this a little bit?
Yeah, of course.
The main thing is also, given we have an algorithm that does something practical, there still needs to be a lot of software. I mean, this is a hidden problem that people don't think about so hard. How do you get people to start using that application? They can't be physicists all the time. They can't have a PhD all the time. You can't expect this from people who have a very good grasp of their domain. And now they have to learn quantum physics too. It's not a request you can make. And that's why they really need to start thinking now. We know what's coming. We know how things interact with each other. we can start developing standards, we can start working on software, we can start making it easier for people to access quantum computers. This is somehow like not talked about enough, I think.
Yeah. In the automotive world, we talk about software-defined vehicles, so it would be a software-defined quantum computer then.
Yeah, that works.
Yeah. Okay, to benefit again from your experience from the application side, so what information or transparency do you require, so perhaps from the providers, but not only from the providers, in order to really make the informed decision on adoption? I mean, these are the question for many, right? When to invest into these, when to adopt quantum computing for their needs. So what kind of information or transparency do we need?
Yeah, I think this really comes back to what I said earlier, that we need some way to evaluate the performances of different hardwares and softwares and everything that belongs into the quantum stack as transparent as possible. And I think this does not work if every provider just publishes their own strange metrics that nobody understands, but really there needs to be a set of standardized metrics that everyone agrees to and everyone understands them. And the results that are provided by whatever providers out there need to be reproducible by the whole community. I think this should be the goal for sure. And as soon as we get there, I think we cannot really say anything about what else do we need, because I don't think that there's anything that we can actually build upon when it's not open source and transparent, right? Because everything that is said by a provider can be misinterpreted or not be reproduced by someone else. I don't think that is of any value. So yeah, I guess there's a long way to go there, and obviously right now it's a wide field of different benchmarking suits out there and metrics, as I said. But the goal should be to unify that in the next couple of years, and to come together as a quantum ecosystem and community, which at the moment, by the way, is a very strong one, I think, and a very collaborative environment in which we are still in. But it will become a competitive environment at some point, right? As soon as we have the quantum computers, and as soon as there is a competition between providers, this will change. And until then, we definitely need this common framework of benchmarks and metrics. That's our way of looking at it.
Yeah, it will be interesting to see, right? Because from the user side, of course, you want it open source, everything transparent. From the supplier side, probably you want to have it locked into your platform.
Obviously,
yeah. We will see who prevails then in the end. But yeah, Nikolaj, as you mentioned, though, you're partnering with Google, and I've seen your publication on PsiQuantum as well. So perhaps question to you, so how can provider side and user side collaborate, work together to accelerate the path from still research, as you mentioned, to coming closer within the 5-year time frame to real use?
So I think collaborating with them and getting closer to the hardware, and also the error correcting stack will help a lot to understand where one can also shave off time eventually. I mean, so PsiQuantum has photonic architecture, so you can do this active volumes, for example. And so there could be also other tricks you could do to make it much, much faster. And I think eventually when we will have the first fault-tolerant quantum computers, or quantum computers which you can run a longer sequence of gates on them, can test heuristics, and this will change the game completely. Because nowadays we can only say, okay, quantum chemistry, we know we have exponential speed up compared, or breaking Shor's, using Shor's code to break encryption. But then if we have heuristics, we can really benchmark and see for certain things that we are faster than classical algorithms. And I think then it will take really off. And I expect this will be in a couple of years that we have machines like that. And then I think then it's even more important that we will work with the providers together, because I mean, without the help of the providers, we won't be able to exploit the machines as good as possible as a user.
Yeah. And do you dare to give a statement which of the technologies around will be the winner?
I have my personal opinions, but yes, I mean, each technology has its problem. So
I see.
And advantages and disadvantages.
Yeah.
It's a race, and yeah, I mean, for big machines, maybe like photonics is very nice. I think even like quantum dots, but maybe the early machines will be ion traps and superconductings because they're much more developed. But we'll see, and the things you learn on these machines, you can certainly then also transfer to other machines.
Yeah. I see. So you have to buy him a coffee then later to get the personal opinion, I see. Very good, thank you very much. So yeah, perhaps a question to you, because you already mentioned that if you want to have a Europe quantum computer, then also European industry, but also all governments have to involve. So what is, in your opinion, the role of partnerships with academia and governments in order to further foster here the ecosystem?
Yeah, it's important that we have first customers to learn how to deploy and how to install quantum computer. If you see at the list of QUTAC member big industry, they all have their quantum experts, like a handful or maybe 10 quantum experts, and all the automotive companies have that, they have their quantum experts, but to my best knowledge, none of those bought any quantum computer so far. Yeah, they have the experts, but not the hardware, which is understandable because we cannot solve industrial problems of industrial relevance. So we need the European HPC centers, we need the research centers, we need the Max Planck Institutes, the Fraunhofers, in order to foster the ecosystem that consists of hard and software and the application. So we need some government funding, intermediate government funding, to bridge the gap between, the early stage and the fault tolerance, which will be, keep us alive for the next 4 to 6 years, until we are ready with the fault tolerance, and then I think we can sell those machines with profit.
Yeah, I just looked. I don't see anybody from the government within the room, so we have to later talk to them.
Yeah, and of course we do. I mean, we lobby, of course. That's also.
Yeah, but we also have to state that the funding in Germany has been quite good. So
yeah.
Also kudos to the government here for pushing this. Yeah, we are coming close to the end. So perhaps as a final question, so perhaps we start with you, Stephen. So what is the one thing which you hope the audience will remember from this panel as a kind of a takeaway message?
Mm-hmm. Yeah, I mean, for me, quantum is coming, no one is stopping. It's not going to go away in the next 5 years. There'll be applications coming. It's about preparing, thinking about realisticness of quantum computing, try to filter out the hype, but also take a little bit of risk too. Like if you're running an organization, have a little bit of budget for startups that we can work together and see, how can we proceed? Because I think the startups are coming with a new perspective. Sometimes they can move faster, they can take more chance, they can, quickly solve problems, but without any risk from the customers themselves. This is like a chicken and egg problem. Like startups can't grow unless they have customers, and the customers are not taking risks, so the startups don't need to exist. And it's so I'm hoping that the corporates that are bigger scale will hopefully buy in a little bit better.
Very good. So it's not an if, but it's only a when. Yeah. Very, very good. Mm-hmm. Yeah. Nikolaj, so what do you want people to remember?
Maybe one thing is that the quantum revolution is going to come. I think but it's slowly. It will come eventually. We don't know exactly when. And maybe 5
years. 5 years.
Yeah, 5 years. It's always 5 years.
5-ish.
Yeah. And one thing I think, if we want to really make it happen, Europe needs to invest more in skills. Mm-hmm. So I think educating people in quantum technology would be very important to really make it happen in a time frame which is not too long. And we can see in the US, they're ahead a little bit in that regards, educating the people in that direction. I mean, it's also happening here, but I think Europe could do a little bit more in that direction.
Mm. Okay, very good, yeah. And what's your key message, Marvin?
Yeah, I think I made my point about open source and transparent benchmarks. I think this is really the key to, especially for the industry and for the users, I think to understand what the current status of the technology is, but even more important, when and what we can expect from the providers in the next couple of years. And obviously we have to do our own job in making ourselves ready for the Q day or the Q sunrise, the quantum sunrise. I also like that idea. Because this will come, as we just heard, and yeah, we need to be ready when it's there.
Yeah, I also like very much the sunrise, and now with the winter coming, right? So we need the sunrise, but it's just the calendar winter coming. Yeah, Ulrich, your closing remark for people to take away.
Yeah, as the other speaker said, quantum is there to stay. So it's going to be successful. It's a question of when, but for research and technology-driven companies, it's important to start investing and investigating now what could be done with quantum, invest in skilled workforce, which is really important, there's a shortage, and have a look at methods and applications which could possibly benefit from quantum. So start your quantum journey now. That's my message.
Excellent.
Thank you.
Thank you very much. So with that, I close it. Thanks a lot for joining. It's been a real pleasure.